So, hello everyone. I'm Ekdeep. I'm technically still a PhD student, but also a postdoc at this point. I haven't officially started because I'm waiting for work authorization. So until then, I'm officially a PhD student. But yeah, I'll be a postdoc hopefully within the next 2 or 3 weeks at Center for Brain Science, Harvard, officially. So the title of the talk that I'll be giving you guys today is Interpreting Emergent Capabilities in Neural Networks. A quick note about me. These are some of the topics I'm currently into. If any of this seems exciting to you, please feel free to reach out. Always happy to chat with other people. And yeah, as viewers, as I was just saying, for now, I'll focus on primarily thinking about emergent capabilities in neural networks. Okay, so when we talk about emergence, in the context of neural networks, this has become like a hype term at this point in recent literature. The interesting thing about this term is, technically speaking, it doesn't quite have a formal definition. Nobody's actually given a formal definition for this, what this means. Primarily, what they're trying to get at is intuitively, just off of vibes, that as you scale some property of the system, let's say you scale data, model size, blah, 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 some capability which did not exist until some critical scale suddenly starts to show up at a scale larger than this critical scale. Like, I'll be very blunt, this is extremely informal, but one thing that's clear is that like this seems to be a phenomenon which repeatedly happens and more so has been observed in the last few years. So to give you guys a quick example, on the left-hand side, this is perhaps like the most popular paper at this point around emergent abilities, where what they show is that like as you increase the model scale, there are several capabilities that the model does not possess until a certain critical scale is hit. On the right-hand side, there is a similar result, which was actually earlier than the Wei et al. Result, but this is on text-to-image models, where what they find is like if you train a larger model on the same amount of data, what you see is a larger model is actually able to like generate images which have clear and precise text written in them. So the ability to write text essentially starts to show up. But there are way more examples beyond these two, perhaps like more popular examples. For example, with respect to training budget, you can get some sort of emergent capability. So for example, in the left-hand side here, we have this paper by Chen et al., where what they do is they train a mass language model, a BERT model. And what they find is that the loss suddenly shows this quite steep jump. And precisely at this point, what they find is that the model starts to get better at inferring the syntax of a given sentence. So this is a syntax acquisition score that they have. On the right-hand side, perhaps like this is another popular example, grokking, and this is perhaps the less useful example, but still a thing that happens. Here, the reason this is less useful is because it's like kind of a multi-epoch training scenario, so like it doesn't, we do not expect this in modern scale models very much. But nonetheless, a pretty interesting thing here that like as you're training a model, the train accuracy hits a fairly high number fairly quickly, but the test accuracy lags behind quite a bit. And until a certain, like you kind of sort of don't know, basically, as you can see, these are individual random seeds, kind of sort of don't know when the model will start to perform well on test data. There are several other examples. This is with respect to data scaling. So on the left-hand side, this is yet another decently known example about induction head formation in context learning. So what's happening is I'm training in this specific paper, it was a toy model, but like let's say you're training a language model, and like fairly early on in training, you see a sudden bump happen in the loss curve. And they can define a progress measure where in this paper, it's called the in-context accuracy, which shows that like precisely at the point where the induction heads form, suddenly the accuracy for a specific in-context learning task jumps up from approximately 10 to 20% to 100%. On the right-hand side, this is a paper we have under submission right now, where what's happening is we take an abstraction of mass language modeling, and what we're doing is we're going to define a simple matrix. We're going to flatten it out and ask the language model to fill in the mass entries. So this is kind of like a matrix completion task. To emphasize, this is not a language model. This is actually a model we trained from scratch. But the point being, you train a transformer from scratch on this matrix completion task. And what you see is that like the loss, which is the mean square error over here, it shows perhaps the sharpest learning curve I've ever seen, having been training these models for a while now. I don't think I've ever seen a learning curve this sharp in my life. So this was quite an interesting thing, like what's going on here. There have been other axes reported in recent works, which go beyond standard axes that perhaps people think about when talking about emergent capabilities. This is context scaling. So what you're doing here is not scaling data or model size or anything. You're simply, in some sense, increasing the budget for inference so that I can put more exemplars into the context. So in this paper, what these guys do is they have cloud, they have like fairly popular frontier models, and then they give them a bunch of exemplars corresponding to behaviors that these models were actively fine-tuned to not engage in. What happens is that until a critical number of shots or exemplars are given, the models will have a basically 0% odds of responding to such queries. But suddenly, after a certain number of shots are hit, you see that the performance starts to improve in the sense that the model starts to engage in these harmful behaviors. While this is a percentage, so maybe like, it's a very discrete and discontinuous measure, you might expect such a sharp increase to happen. You can actually look at the loss curves that these guys report as well. And you can see that like the loss curves show a precise change in the slope. This is very reminiscent of how people think about a second order phase transition in physics. You have two curves, basically with respect to some scaling, and until a certain critical scale is hit, the transition, until a certain critical scale is hit, the curve basically will have a certain slope, and as soon as that scale is hit, the curve starts to turn in a completely different way. Okay, so up to this point, I just wanted to establish some motivation that like this is a phenomenon. It's perhaps a phenomenon that like you see time and time again, but I don't think as of yet, like it's been fairly well recognized that like if you collate it in all these different papers, you'll see that like it's much more pernicious than we appreciate, in my opinion. And the thing is that like, okay, this is a phenomenon, but like, why should we care about this? And the place where my motivation for this comes from is thinking about AI regulation. So there have been a bunch of frameworks proposed for AI regulation recently. The EU AI Act, there was the Blueprint for AI Bill of Rights from the White House, the NIST AI Risk Management Framework. And all of these frameworks are grounded in risk regulation. The motivation is quite simple for why you would want to do a risk regulation framework, because it's difficult to define causality when you have a AI-like system. Like, for example, if a self-driving car kills someone, is it the car like, is it the fault of the car? Is it the fault of the AI developers? Is it the fault of the research, like beyond the research community and like maybe the software people who develop the software? Is it the fault of the driver who was sitting in there? Or is it the fault of the person who maybe like mistakenly walked in front of the car? It's difficult to define causality in those situations. And so the thing with risk regulation is that risk essentially what it means is that like I will assume, I will speculate what harms can possibly be caused by my system, and then try to define regulation which dissuade said harms to occur. And in some sense, what this assumes is that I can predict what the harms are. I can predict what capabilities my system possesses, which is literally what emergence stands in the face of. The whole point of emergence is, as of yet, what people have been looking at, it's kind of an unpredictable phenomenon. That there are like the way I try to think about this is that there are two ways you can decompose emergent capabilities. There are unknown unknowns, that there are capabilities I just don't know my model will possess. And like maybe it possesses, even like maybe current models possess certain capabilities which may be undesirable in my opinion, but I just don't know what they are. And until they show up, until somebody faces the harm caused by said capability, I just don't know what to do with it. I just don't know that it can happen. And another decomposition here is an unknown known, where like perhaps I know that my system can, like I suspect my system might cause a certain harm, but I don't know until what scale that capability will show up. So even if I know what that capability, like even if I can speculate what said capability is, it's difficult for me to do the relevant risk assessment because I don't know how to trigger that capability. I don't know at which scale it shows up. So it's very easy for like under risk assessment reports for such a capability to just slip through. If none of that motivation clicks with you, perhaps just scientific curiosity is also a sufficient motivation to pursue this agenda. So yeah, this is our goal. We want to understand how emergent capabilities occur in neural networks. And several barriers that we might have to get past for this is like we perhaps need to first define what we mean by emergence in the context of machine learning. What drives these capabilities under a reasonable definition? Like, what are some viable hypotheses? Is it just perhaps the some hypotheses that people have speculated around is that maybe it's just the metric? We have bad evaluation protocols which are very discontinuous. So, like, let's say if I only reward you a score of 1 when you do a certain task, and like I completely reward you 0 when you don't do a certain task, until you hit the point where you're completely accurate on the task, your performance will be 0, and then suddenly it shows up to be 1. So intuitively, okay, makes sense. Maybe like it's a metric thing. But I'll show you a large number of results that that's not the case. There is inherently, truly something fascinating going on under these models, in these models. And there are other questions, perhaps, what we should also keep in mind, that like emergence, as I was showing in the motivational slides, that like this is not a singular phenomenon, perhaps. There are multiple axes going on here. If you increase the model size, the amount of data, the amount of context, it's unclear if all of these come under the same, if a singular hypothesis can explain all of this. And this is perhaps something we might have to keep in mind as we pursue this agenda. Okay, so these are the 3 projects that I'll be talking about today. The first one is something we published at NeurIPS last year. The second one just came available on arXiv. And the third one, we're still working on it, and hopefully it will be on arXiv soon. So yeah, I'm quite excited about the third one as well. So hopefully we can get through all of this. But if at any point it seems like I'm about to go over time, just let me know. Cool. Okay. So I just also want to mention, if anybody has any questions, please feel free to jump in between. But at this point, I'm happy to take like a 5-second pause if there's any question. Cool. Okay, so the first paper, compositional capabilities emerge multiplicatively. In this work, what we argue is any capability which is a composition of some underlying atomic abilities will show an emergent learning curve. So what I mean by that is, what do I mean by composition? Let's say you want to make an image of this sort, an astronaut riding a horse in space. So this is an image made by DALL-E 3. What you can see happening here is that, like, to get this image right, not only does the model need to understand how to make an astronaut, not only does it need to understand how to make a horse, it needs to understand what riding means, what that like an astronaut needs to be riding said horse. In space, perhaps implies that like we need this that this is a fairly unusual thing to happen, and perhaps we won't have a natural horse in this kind of a setting. So even the horse perhaps needs to look somewhat majestic, somewhat more fancy than a standard horse would. And you can see like the model is getting and capturing properties of that sort. From this point of view, however, let's say your model doesn't quite understand what it means, what like images in space will look like, then it made just this image on some sort of a land or like Earth-like background. In that situation, you would penalize the model and like not give it appropriate credit, which is the right thing to do. It's like, well, it got the concept of space wrong. So until the model actually starts to understand individual concepts, it acquires the ability to create concepts corresponding to individual or images corresponding to individual concepts, it won't be able to create the composition of said concepts. So that's broadly the intuition. And to empirically analyze this will take a very standard approach that people take in natural sciences called the model experimental system approach, which is to say, rather than looking at astronauts riding on a horse in space, we're going to look at shapes and colors. It's a strong simplification, but I'll show you a lot of results that kind of sort of seem to indicate anything we'll talk about will generalize to real data as well. So what we're going to do is we're going to first create an abstraction of text to image model training, where I'll show an image of this sort, and I'll give a tuple instead of text. The tuple here, for example, is 1, a, in this case, 2, a, 1, b. And I'm going to ask the model to generate an image corresponding to a tuple it has never seen before. So what's happening is when I'm asking it to generate and when I'm training it, I'm training it to generate red circles given 1, a, red triangles given 2, a, blue circles given 1, b. But I'm going to test it for 2, b, which, as you can see, because a is common here, it probably means a is red. Because 1 is common in these two, it probably means it's a circle. So probably 2 means triangle. So 2, b probably means a blue triangle. So what we're going to have in this system is that like these images or these tuples will never be shown during training. So the model truly has to infer the concept of color and shape and figure out how to compose them. So this is an entirely outer distribution generalization task. And we can now formalize this a bit more and slightly make it more complicated. So what we're going to define in this paper is a framework that we call a concept graph. Basically, say you have a bunch of concepts like shape, color, size, location, angle. What we're going to do is we're going to take a subset of these concepts and give them precise values. So like circle, small blue, triangle, large red. And these things, once they're given precise values, we'll call that a concept class. So to emphasize, when you create a concept class, certain variables remain free. So you can essentially give any value to those variables, but all samples with the first 3 values fixed to be, let's say, circle, small, and blue, will belong to the same concept class. So you can think of it this way, that like every sample that you get from a concept class will be an object of that class. And if anybody from a CS background is hearing this, you can see this is basically talking about object-oriented programming. This is a class, and this is an object which is inheriting the properties of that class. What you now get is that you can organize these concept classes on a graph, where the graph basically has edges which represent specific concepts. So here, this edge represents the concept of shape, where like if I go from the left node to the right node, the shape changes from a circle to a triangle. Similarly, if I go along this axis over here, the size changes. And if I go along this axis, the color changes. What I'm going to do is I'm going to only show the model a few of these concept classes. So for example, these 4 nodes over here. So samples in the training data will only come from these 4 nodes. But the remaining 4 nodes are entirely unseen by the model. The model has never seen what a small blue triangle or a large blue triangle looks like. It just has to figure it out on the fly. So this is basically, and like we provide some formalization around this, and it's also extremely related to a concurrent work which came out from Sanjeev Arora and Anirudh Goyal from DeepMind, called the Theory for Emergence of Complex Skills in Language Models. Just that we have much stronger empirical results. So yeah. So to be clear, this is not exactly an insane abstraction. For example, if you simply take clip models and you look at the representations of clip given these prompts, red strawberry with white background, red banana with white background, and so on, what happens is if you simply do a 3-dimensional PCA, you'll find that you actually have a concept graph in clip itself. So to emphasize, this is not an insane abstraction. This abstraction perhaps is fairly decent. And real models already are entering this abstraction, or like this abstraction is fairly faithful with respect to real models. Okay, so to look at some results now, what we're going to first do is simply see whether the model generalizes at all. So here, again, remember, we have these blue nodes, which we will show as part of the training data. So like the large red triangles and large blue circles and so on. These pink nodes are what we don't show in the training data. The pink nodes with a distance of, where like only one concept has to change. So like this node corresponds to a change of size. We call them to be a distance 1 away. So in the sense that these tuples are Hamming distance 1 away. And this pink node has a distance of 2 with respect to the training data, as in the closest node in the training distribution corresponds is at a distance, Hamming distance of 2 away. So here is the training run. It's going to take a while, but you can see that the model kind of sort of picks on shape fairly quickly and size as well, but kind of sort of is still struggling with color and kind of sort of starts to get hard at some point, but still keeps going back to the red color. At this point, you might start to see that like these first three nodes, they are, not sure how to make this go away. But yeah, the first three nodes have kind of sort of converged, but the node at distance 2 away is still somewhat changing in its color. And if you just let it train for a while, you'll see that like it does converge finally to always being closer to a blue color node. So first thing first is that something that was completely out of distribution, the model did generalize to that. But now what we care about is looking at the emergence, the notion of emergence, for which what we're going to do is we're going to look at the learning curves. So here on the x-axis, I have optimization steps. Sorry, this is like multiplied by 1,000. And then on the y-axis, I have the accuracy. So the way accuracy is computed here is like a fairly standard way of doing this in the literature on disentanglement, where what we'll do is we'll train linear probes on the outputs generated by the model, and like each probe corresponds to an individual concept, so like color, shape, size, and the accuracy will be defined as whether the model gets all the shape, size, and color right or not, corresponding to individual concept classes. So these are what the learning curves look like. The blue learning curves, again, correspond to the train distribution. The pink ones correspond to the outer distribution datasets, distribution concept classes. And what you can see is it's quite fascinating that like the model gets the blue learning curves right, the concept classes seen in training data right fairly quickly. But if you just let it train, sooner or later, it starts to actually generalize to outer distribution classes. And it actually respects the data structure as well. So it first generalizes to concept classes which are a distance 1 away, and then it generalizes to concept classes which are a distance 2 away. And it generalizes fairly quickly to concept classes which are a distance 2 away, in the sense that like fairly suddenly the learning curve starts to improve. And this is very reminiscent of what we saw before, that the learning curve or the scaling curves for model scaling for the Wei et al. Paper, the Emergent Abilities Language Models paper, you see that their performance suddenly improves. So this is all to say the class which required composing concepts as part which underlie the training distribution, the model has to first infer what those concepts are, has to learn to compose them. The more compositions involved, the more sharp the learning curve gets. And in the paper, we have like concepts which are so like this is just three concepts right now. We have 4 concepts and 5 concepts as well. And what you basically get is the learning curve keeps on getting sharper and sharper when you have to go more and more outer distribution. So what's going on here under the hood? What we can do is, because this is a synthetic and control system, we can actually analyze how the model is improving in terms of individual concepts. So when you look at the shape, the size, and the color, as plotted over here, you can see that the model's improving on shape fairly smoothly, on size kind of sort of smoothly, and on color, it fairly drastically changes. In the sense that the model was struggling, and at some point, it started to learn how to model color as well. If you wanted, you could have, technically speaking, defined an eval, which was additive in getting all these 3 concepts right. And you would see that like that additive eval would have a much more smoother scaling curve. But in actuality, what you care about is an and condition over these concepts rather than an or condition. What I mean by that is like, if the model has to generate small blue triangles, unless the model is creating triangles which are small, or it is creating triangles which are blue, it doesn't make sense for me to give credit to the model. Truly, to get this concept class right, you just have to generate, you just have to get all the 3 concepts right. And from that point of view, the right kind of eval is an and operation over all the individual concepts. And when you get the and condition over all the three concepts right, you can think about that as like the composition is getting right. And as the composition is right, you see that the accuracy suddenly will suddenly start to improve if one of the concepts is bottlenecking the model from getting the overall composition of concepts right. So in some sense, the idea is that this multiplicative evaluation underlies the sudden emergence of capabilities that we see under input when we prompt the model to generate samples corresponding to outer distribution classes. And basically, this composition should be thought of as an and operation over individual concepts. Interestingly, when you perform some minimalistic mechanistic analysis of these models, you see that at the point where the transition, so to speak, starts to happen towards getting the concepts right, if you intervene on the internal representations of the model, you can actually get the model to generate basically anything you want. So if you wanted the model to generate like a different shape, you can actually see like you can interpolate between the circle and triangle and get actually not just a circle and triangle, but something that's kind of sort of an interpolation between them. Similarly, you can interpolate between different colors and different sizes. What I'm getting at here is that truly the model has learned disentangled representations as part of this compositional generalization task, which is what is leading it to basically being able to solve the outer distribution generalization problem. And yeah, apparently this was quite a surprising result to people working on disentangled representation learning, because there's a giant set or series of impossibility results in generative modeling for disentangled representation, which shows this should not happen. So those guys were quite excited to see that this works. So that's that. Okay, so quick discussion about this first project. Emergence is partly driven by compositional properties. That's a hypothesis we claim, that when you when you have capabilities which are compositions of individual or some sort of primitive atomic concepts, you'll see that their learning curves can suddenly grow. And that sudden growth happens because individual capabilities have to get right before you can get the overall composition right. It's an and condition over each individual atomic capability. We have several more results, some realistic evals on Celebi datasets as well in the main paper. And I quickly want to give a shout out to the Big Bench paper, which actually had a tiny note in the 100-page paper saying tasks that see strong breakthrough behavior in their empirical analysis were generally composite in nature. They didn't have any analysis or like any precise results, precise experiments which show that this claim is true. This is just speculation that they have. So our results in some sense vindicate this statement that indeed things which are compositional in nature will show certain breakthrough or certain emergence like learning curves. So yeah, that's the first paper. Before I go on to the second one, which is going to be a follow-up of this first one, if there are any questions, happy to take that. No? Okay. I see something in the chat, actually.
Yeah, there's a comment.
Cool. Okay. Nice. Yeah, we're actually looking into board games right now. I just came from a meeting where we're hoping to use board games for expanding on this work. So yeah, great idea. Okay, cool. So this is the second paper that I wanted to talk about. This is titled Emergence of Hidden Capabilities, Learning Dynamics in Concept Spaces. So this work is quite an exciting follow-up to what I just showed you guys. Here, what we do now is, in the previous work, we were simply prompting the model to produce an output. Now, what we're going to do is we're going to define a thing we call a concept space, where a concept space is something like this. Let's say your learning task is these small red circles, small blue circles, large blue circles, large red circles. So similar to before, just like this is just two concepts now, size and color. And let's say as you're training your model, you look at its generations, and let's say the color is somewhere between red and blue. What you can do is you can take that color and you can map it onto like where that color lies between this on this axis. Meanwhile, let's say the size is somewhere between large and small. So you can take that size and map it on somewhere over here on the y-axis. When you do that, you basically, what you're doing is you're mapping the model's generations into this coordinate space, this abstract coordinate space that we call a concept space. And what you can now do is, like, as the model is going through its learning, you can, as the model is being trained, you can actually map the entire learning dynamics onto this 2D concept space. And what you find as a consequence of that is learning curves which look like this. So this is where the model was initialized. And as you go through learning, you see these rather interesting learning dynamics where, like, take a step back. The first three, these points over here, these nodes over here, these are what we showed during training. And this one node over here, this is which is kept out of distribution, as in, like, it's kept out of the training data. So the model has to truly figure out how to compose the concepts and generalize to this fourth node over here. And so what you can do is you can capture the learning dynamics for both an in-distribution class. So for example, the class 0, 0 over here, and an outer distribution class, for example, this class over here. What we find now is that, like, as the model is learning, as it is going through its training process, the learning curves show this interesting trend where, like, first they go towards this side, these learning curves, they go towards this concept class, and then, like, they suddenly turn and start to go towards the concept class 1, 1. As in, they start to create samples which correspond to small blue circles. This is kind of a fairly wacky learning curve, I would argue. And what we find in this paper is we can actually define a fairly interesting measure called the concept signal, which allows you to even control which direction the model first goes. Like, whether it first starts to go towards, let's say, the small red circles, even when you prompt it to make samples corresponding to 1, 1, whether it starts to go towards 0, 1, or whether it starts to go towards 1, 0. And meanwhile, when you look at the in-distribution learning curves, you see that the in-distribution learning is fairly smooth. It directly goes towards the concept class that you showed in training. So it seems like something interesting is happening, that, like, these learning curves indicate that, like, some sort of interesting transition-y behavior is going on around these sudden turn points. And as it so happens, you can define a fairly simple system, a simple differential equation which captures the geometry of these learning curves. The idea here is fairly simple, that you basically just assume that there's going to be a turning point. You define a simple potential function, which is kind of like a sigmoid, where the idea is that, like, as you go through, like, you can think about how a sigmoid looks like, that, like, there is a slope period in the sigmoid, the first half, and then, like, there is a sudden growth period, which you can think of as a certain transition point, and then there is a fairly smooth and slow period again. So I'm not saying this is a true phase transition or anything, but, like, I'm just saying this captures the spirit of that. So perhaps if we started looking at this point over here in when the model is around over here, we might see something interesting. And that's basically what happens in our results. What we find is that when you simply naively prompt the model as it is going through learning, you'll see that, like, if you simply naively prompt the model, in the sense, like, if you simply ask it to generate images corresponding to, let's say, 1, 1, you'll see that the learning dynamics look like this, that the model basically never creates the right sample that you want, which are, like, small blue circles. But if you were to perform some sort of a latent space intervention, or, like, some sort of an input space intervention, which I can describe in a second, you'll see that, like, precisely at this point, this was the point where that sudden turn happens. Precisely at the point of sudden turn, the model actually starts to create the right samples that you want, which is to say small blue circles. What this indicates is that like precisely at that point, the model had actually disentangled the relevant concepts. It has very quickly, it learns how to compose said concepts. And as of yet, it just doesn't know, it just hasn't mapped the input space, the input of 1, 1 to the instruction of 1, 1 to the specific sample that we wanted to create, which is a small blue circle. So it's kind of an interesting and like fairly important point, in my opinion, around generative models in general, that when we take modern generative models and we simply prompt them as we generally do in their evals, we're kind of perhaps missing out on several capabilities that they might possess. But we're missing out on that because we just don't know what the right prompt is. And essentially, benchmarking and prompting in the sense are like hiding how competent the model truly is, which is, in my opinion, a somewhat of a scary thought that like the models might be much more capable than we expect them to be. So yeah, and there are some results that we have in the paper now to show that our results do generalize to realistic data as well. So there's just like a very quick example of that. Here, what I'm doing is I'm taking the Celebrate dataset where which is just images of celebrities. Here I have a man without a hat. The concept classes here will be defined as genders and whether the person is wearing a hat. I know the data is kind of weird, but we needed something that was like properly labeled so that we can create the experiments that we want and define these concepts. So here you have a man wearing a hat, woman wearing a hat, and just a woman not wearing a hat. What we're going to do is we're going to train models on these 3 concept classes and hope that it generalizes to the 4th concept class, which is outer distribution. What you see are learning curves of this sort, learning curves corresponding to the in-distribution task, as in creating image of man without a hat, woman without a hat, or man with a hat. The learning curves are kind of sort of smooth, but the learning curve for the outer distribution task of creating an image of a woman wearing a hat doesn't succeed. The model does not generalize under naive prompting. And the learning curve is kind of wacky. It's going all over the place. And it finally converges to this, what seems like to be the closest concept class in the training data of just a woman without a hat. However, if you perform a latent linear intervention, which is similar to the latent intervention that I was talking about before, if you go into the model's latent space and intervene and basically pressure it to create images of women with hat, you can make the model do that, even though with naive prompting, you cannot. So I feel like this is like a fairly strong result, in my opinion, that like people do expect that models probably possess more capabilities than we're able to elicit out of them. But I think like this result like fairly concretely shows that even the models of the past, not necessarily the frontier models or like more fancy systems, already possess capabilities beyond what we were able to evaluate them for. So yeah, broadly, the takeaway of this project then was a hypothesis that we converge on based on our experiments. Our generative models possess a lot of hidden capabilities that are learned suddenly and consistently during training. I say consistent because across several random seeds, we consistently found that precisely at the same iteration, or well, technically in about 100 iterations of the same point, you see that the model learns these hidden capabilities. Like if you perform later interventions, you can make it elicit an output that you desire. However, naive input prompting may not elicit these capabilities, hence hiding how competent the model actually is. This notion of competence is fairly commonly used in cognitive science as well, where we try to distinguish between between the notion of competence versus performance, where performance is more so like if I give the right environment, if I push the system into the right environment, I know for a fact it will show the capabilities it possesses. And that situation, how performant the model, the system is, versus competence, which is like the system might possess capabilities, but it's just like we're not necessarily until we have the necessary and right environment, it has no pressure or no incentive to show those capabilities, even though it possesses said capabilities. And our argument is something of the similar sort is happening in modern generative models. And yeah, as I was saying, arguably the community expects this now. But what we show in this paper is that even toy systems can capture this behavior. And these toy systems are actually fairly amenable to analysis. We'll have a theoretical follow-up coming soon, which shows a thorough characterization of this behavior. So yeah, this was the second project I wanted to discuss. And one final project, which is still a work in progress, but something I'm fairly excited about, is titled this way: Emergent Language and Reasoning Acquisition in Neural Networks Trained on Formal Grammars. In case there are any questions, happy to take that now. Otherwise, happy to go on. I see there's somebody asking about how does this relate to goal misgeneralization. It'd be helpful if you could point me where this question came to your mind from. How can we guide the emergent behaviors? Okay, it would help if you can speak up, and maybe we can maybe I can get your meaning better. Okay, how can we guide the emergent behaviors?
Yeah. Sorry, I just want to say sometimes attendees are in public spaces or something and cannot speak.
Oh, okay, I didn't know that. My bad. Okay, yeah, cool. So yeah, how can we guide the emergent behaviors to be in direction that is more on the useful side? As of yet, I don't think we have a good idea around that. Like the more broader point of the research agenda I've been trying to follow is that like let's try to capture broadly what the behavioral signatures are of capabilities which show emergent learning curves, so that we can start to figure out what the right evaluation protocols are. For example, in the first work, when we show that like there's a compositional nature to like capabilities which show emergent learning curves, the idea in that paper, or like the more practical observation from that paper then, is that like if you can define a decomposition of the overall task, and you can track the learning curves corresponding to the decomposed capabilities, the atomic capabilities, then you have a better shot at guessing when the model will be able to compose said atomic capabilities and hence generalize completely outer distribution, or like show a capability that you expect or that you do not want the model to possess. So in some sense, the idea or the main takeaway from that paper from the point of view or the practical point of view of defining better evaluation protocols is do not just track the capability you care about, track capabilities which are instrumental for the overall compositional capability. So from that, from all of this point of view, the idea is that like we don't necessarily know how to guide these systems towards different behaviors yet. What we do know is, or what these analyses are getting at, is different hypotheses for which capabilities will show emergent learning curves, and under the assumption that you follow a standard training pipeline as people currently do. Yeah. I don't know if that answers the question. Is it possible? Oh, okay, cool. Yeah. So okay, there's a question still on the paper number 2. Did your research look at various network sizes and how that impacted performance? Any intuitions about mechanistic interpretability around when the capabilities emerge? So not in this work per se. We don't necessarily look at the effects of model size. This is only the effects of scaling the data, and because that's a slightly easier thing to study. I do have some. We have some results for a project which is still work in progress, where we actually are able to get emergence with respect to model scale as well. To my knowledge, that's actually the first result demonstrating emergence with respect to model scale properly, and even though in a synthetic system. So yeah, as of yet, we don't have results on the effects of network size. That being said, in regards to the mechanistic interpretability part, this precisely was the mechanistic analysis. What we were doing here is that we were interested in why these sudden turns that we see in these learning curves happen. And the hypothesis was that like perhaps the model has, in the spirit of physics, undergone some symmetry breaking, which in this case would be like it has disentangled the relevant concepts. And if I go at that point and I start to like just force the model by doing some latent interventions, which is the standard, which is a fairly standard protocol or standard tool you would think about in the context of mechanistic interpretability, we would perhaps be able to make the model generate samples of this class, which we are currently not able to do if we simply naively prompt it to generate those samples. But if I perform latent interventions, perhaps I'll be able to do that. And that hypothesis checked out, as you can see, fairly well. Basically, in about like about 10% more iterations after this turning point, and this is exactly the turning point, you can see that like the learning curves suddenly grow to be an accuracy of 100%, and the model generations are clearly shown over here. The model is able to generate small blue circles. So the way I think about this is that like this was not a mechanistic analysis for like how the model is composing, but it was us using mechanistic interpretability tools to create an analysis of the learning dynamics. So the objective study compared to standard mechanistic interpretability was slightly different. We were not trying to reverse engineer algorithms for how the model performs the task, but like get better insights into the learning dynamics of the model. But yeah. And I guess like I didn't perhaps clarify this part very, very clearly, but this is in some sense what's going on over here is this is an intervention in the latent space, and this is an intervention in the input space, where what we're doing is we're literally searching or doing an exhaustive search over all possible inputs to identify the inputs, which will lead to a small blue circle. So this is impractical. This is not something you would do in a real model. But the idea is that like here in this toy system, we could do this, and we were able to like get some input which generated small blue circles, which is to say that like there existed some input. It was just not the input we expect the model to generate small blue circles for. Cool. Okay, I hope that answers the question. Yeah, so the final project I wanted to talk about, emergent language and reasoning acquisition and neural net trained on formal grammars. Okay, so similar to the spirit of the last two projects, where we were studying basically toy model systems and trying to look at emergent capabilities there, this time we'll define a more language-like domain. Precisely, we'll define a formal grammar, which will be a context-sensitive grammar. Specifically, what you do here is you define a fairly simple grammar which has structure or symbolic structures like these. You have a modifier, a subject. It's kind of a stretch to call this a modifier. That's technically a determiner, but bear with me. And let's say you have a conjunction, another noun. So you have a sentence, let's say something like this, the man and the dog. And then you will have something like a verb phrase, which is which can be of different sorts. Modifier with a descriptive property is very happy. Modifier with a verb with another conjunction and a verb, runs quickly and jumps, and so on. So in a standard way, how in formal grammars people define symbolic rules which control the underlying syntax of the grammar, we're going to define such rules. This is not exactly a depiction of the rules, but like to indicate like what some of the rules will look like. And when you sample symbolic sentences from those rules, you can fill in those sentences. We will fill in those sentences with specific terminal variables, which in this case are things like the man and the dog is very happy. And what we're going to do is, if you simply define syntactical rules, those will lead you to what's called a context-free grammar. But we're going to define what's called a context-sensitive grammar in the sense we're going to impose type constraints. So if I have a subject and if I have, let's say, a property, I'm intentionally going to constrain which subject shows up in the context of which property. So for example, a man can be happy, but a man cannot be ringing, similar to how a telephone can be ringing, but a man cannot be ringing. So this is a depiction of the type constraints as a bipartite graph. So I'm going to define, similar to what I was doing before, a concept class. This is the class of humans, let's say the class of animals, class of furniture. And each of these nodes corresponds to an individual object in that class, or an individual entity in that class. And each entity will have its own properties. So like, let's say humans have age, they have a name, they can walk, they often have a job, they have pronouns, blah, blah, blah. Similarly, for animals, they might have properties like age, name, walk, pronouns. They have generally some sort of specific sound. Meanwhile, furniture has very different properties. It has generally some sort of color, material, height, blah, blah, blah. So you can create sentences here where generally we will intentionally impose constraints that like entities which belong to classes which we call subject classes will show up as a subject. So for example, man, and man has the ability to walk because that is a property man possesses. And then let's say you had a class like road, then we would say we can create a sentence like man walks on road. So overall, the idea being that like this is supposed to capture a very minimalistic notion of what semantics looks like in the context of natural language. And broadly, the context-free grammar will capture a notion of syntax. So what we're going to do is we're going to define 3 tasks here. The first task is simply free generation. I'm going to just ask the model to generate sentences and just check whether the sentences are grammatically correct and whether they follow the type constraints or not. The second task would be word unscrambling, which is a slightly more reasoning-oriented task. But what I'm going to do is I'm going to give the model a sentence which is scrambled, and I'm going to ask it to generate a unscrambled version of the sentence. And to emphasize, this is actually a task that even large models on scale show emergence, as in like the frontier models show emergence for. That was actually precisely the reason why we chose this task. And then we have a task called conditional generation, where what we're going to do is we're going to give 2 specific words and ask the model to generate some sentence which is grammatically and syntactically and semantically correct to compose these 2 words. And this is what the learning curves look like. Our first result is actually you can get emergent properties even in this fairly simple system, where what I'm going to do is I'm going to train models on sentences sampled from these grammars. And fairly consistently, what we'll see is, so these are 2 tasks, the unscrambling and the conditional generation task. And these are 2 metrics that I have, the first metric is called exact match, where if I go back to the unscrambling task, the exact match is saying like, is the unscrambled sentence generated by the model perfectly every token matches, as in like the model literally said it is only to be understood in the scenario. And we'll have another metric which we call the per token accuracy, which will be like if I get the first token right plus whether I got the second token right plus and so on, and then I take an average of that. And finally, the conditional generation accuracy will be defined as what we call the constraint accuracy, which is whether the first word and the second word were in the sentence and whether the sentence was grammatically and semantically correct. The product of all those things will be given a credit of 1. So yeah, this is what the evals look like. We find fairly consistently that like regardless of whether we're looking at the unscrambling task or the conditional generation task, there is a certain point where, like, for example, here the per token accuracy increases a little bit for unscrambling. This is precisely the point where we see that the model is starting to generate syntactically correct sentences. Then there is a second point where the learning curve starts to improve for, let's say, the exact match accuracy for unscrambling. And similarly, the constraint accuracy starts to improve for conditional generation. And precisely at this point, what we find is that the model has internalized the type constraints. And to emphasize, we do not show the model all the type constraints. As in, like, the model has not seen several subjects in the context of several properties. It truly just has to infer them on the fly in an online manner. Then we have like some other tiny learning properties, like you have to learn about modifiers and stuff. And then as you keep going through training, there is this really interesting and exciting jump that happens in the performance for unscrambling, where what we find is that the model starts to generalize to longer sentences. So first, it can only solve this task for shorter sentences, but then like there is a certain point where, fascinatingly, the loss reduces by 0.02 bits. It's an extremely tiny change in the loss. It's a very sharp, you can see when you look at the loss curve, you see that it's a very sharp staircase-like jump, but it's a very tiny jump. And at that point, the accuracy for the unscrambling task increases by about 15%. So what happens at this point in this length generalization result, and again, like this is a work in progress, so like these curves are just for a single seed. When we perform multiple seeds, it'll slightly smoothen out. What happens is that the loss changes by 0.02 bits, because what the model starts to do correctly is, for unscrambling as well as the conditional generation task, it starts to get the verbs right. So if you think about it, let's say you have a sentence which is simply, man is tall, which is a very short sentence, but it just requires for you to know the properties of the sentence. It's easy for the model to learn those sentences compared to sentences which are like, man is tall and is walking on the road, where like you have to get the conjunctions or the verbs right to compose a sentence which involves a subject phrase and an object phrase. And precisely at this point, what's happening is that the model starts to get these conjunctive symbols of conjunctive concepts from the grammar, right, which allows it to generalize to longer sentences. This is another result on the conditional generation task, where what we find is that like because we define a set of constraints on which concept or which entity has which properties, what you can have is that as the model is learning, you can look and ask it to generate sentences where you give it a specific entity, let's say man, and then you give it a specific property, let's say runs, and like it's able to create those sentences, most likely because it has seen that a man is able to run. But let's say you ask it to create sentences like astronaut, and where the word astronaut composes with the word run. So like creating sentences of the sort where astronauts are seen running, like this is probably something you've not seen in your training data. And what we call this this notion of distance here is slightly different compared to the previous notions that we talked about. But here what we say is that like as the model is going through training, these are distance one classes are classes which have slightly more shared properties with respect to the original class. So like man versus astronaut, they will have fairly giant number of shared properties, but not all the properties will be shared. So we bin the number of properties, and according to the bin number of properties, we define a notion of distance. And what we'll find is that like the model starts to generalize to these outer distribution combinations that were not seen before during training, for example, astronauts and runs. And similarly for distance two generalization as well, like you'll see that like the generalization starts to happen sooner or later for even classes which are more outer distribution. And it is again following the structure of the data, that first it generalized to distance 0, then to distance 1, and then to distance 2. And if you just let it train further and further, you'll see that like performance improves quite a bit for all the combinations. And what we show is that the transition point that we saw for this is the first result, that like the transition point that we saw for the first point where the model learns about semantics, as in the type constraints, you can actually map it onto a scaling curve. So here what I'm doing is I'm changing the number of properties shown in the training data. And as I'm increasing the number of properties, the accuracy on these descriptive sentences, so for example, the short sentences of the sort, man has property. So like, object has property. So like man can walk, man can talk, something like that. You can see that the performance improvement with respect to the number of properties if you divide the training steps by the number of properties to the scaling exponent of 1.5, all the curves collapse onto each other. This is truly reminiscent of how you would think about creating phase change plots or phase transition plots in physics, where what this is indicating is that if there is a transition point which follows a specific scaling trend, then if we divide by that the specific scaling trend, then all the curves, all the curves which demonstrate the properties of the system should collapse onto each other. So perhaps there is something systematic going on, even in this fairly simple grammatical formal grammar setting that we created. And another interesting thing, which is quite fascinating to watch as well, is that like after the transition point, all these different models with different number of properties, they show a fairly linearish growth trend in the accuracy. Is there a theoretical model which can capture these results? And we argue there might be. So what you can think about, going back to the way this project we started discussing the motivation of, you have something like concepts or entities, man, astronaut. Then you have some verbs or properties for those concepts, so like man, horse riding, astronaut, walking. And you see combinations of these properties in the training data. As I was mentioning before, this was like a bipartite graph, where on the left-hand side, you have entities, on the right-hand side, you have properties. As you keep on training, you see more and more training data, and at some point, you start to learn that, okay, man can horse ride. So like this entity connects with this property. And as I see more and more training data, perhaps I start to learn that, okay, the properties which go together. So for example, this entity which connects with this property, this entity connects with this property, this entity connects with this property over here. And like perhaps I start to learn properties which I do not as of yet have seen any training data for, which connect with a specific entity. I start to learn how to fill in those missing gaps. And this is going to be very reminiscent of like, as I keep on adding more and more edges in here, this is very reminiscent of how percolation, the concept of percolation happens on a random graph, where like basically as more and more edges are added onto this bipartite graph, at some point I start to understand that all the entities on the left-hand side can basically be connected to all the properties on the right-hand side, even though I have not seen any explicit training point which indicates to me that these should be connected. And like in the context of percolation on a bipartite graph, so you can think of this as like, what is the largest cluster size that exists on this bipartite graph? And if I look at the edge density, you see that we know theoretically that like the percolation problem on bipartite graph shows a phase transition where like suddenly until a critical amount of edge density, you do not have the largest cluster size is basically 0. But then after that critical density, the largest cluster size starts to increase in this square root kind of scaling sorts. This is very intuitively very akin to like a memorization to generalization phase, kind of sort of like grokking. And as it so happens, this scaling curve, we know that it follows a square root scaling trend. So basically, the transition point, it scales as square root of number of properties or the number of nodes on both the left-hand side, right-hand side of the bipartite graph. This would, technically speaking, indicate that if this model is correct, this would indicate that like the scaling exponent should have been 0.5. But what we saw was the scaling exponent was 1.5 for our the reasoning task that we defined in our formal grammar. 1.5 scaling is unnatural so to speak. It is an extremely large exponent, and it would imply that generalization is hopeless for neural networks. So we think this is perhaps like there is some quantitative mismatch right now if we were to go use percolation as the model for explaining these transitions. However, given that there is a broad qualitative match where in the way the model where the percolation model thinks about basically the phase transition happening according to the largest connected component, and like how we see the learning curves check out in our experimental system. We see that like after that transition point, there's a fairly linearish growth of the scaling of the learning curves in our model. So given the qualitative match, we expect the theory might actually have some promise. And possibly the issue right now is that like our object properties graph are being defined with a distribution which is not correct. So perhaps we need to like look into different distributions for the way the type constraints have been defined. So yeah, this is still very much a work in progress, but this is the rabbit hole we're going down under to explain the transitioning behaviors that we've seen and the plots that I showed before. Okay, yeah, so that was my last slide. If there are any questions, happy to take them. And yeah.
Hello, I think I missed how the model could infer the connectivity because you said the data didn't show the connection. So I think there was a point there that I missed.
Yeah, sure. Okay, so the thing is that like how the data can infer the connections is that like, okay, so to begin with, the graph is fairly sparse. As you're performing, as you're adding more and more data to this, or as the model is seeing more and more data, the model starts to perhaps like infer that, okay, these two things are connected. The connections which it has not seen before, as of yet, it's not able to infer that. But when you show it more edges, for example, you show it, let's say, this node is connected to this node over here, this node is connected to this node over here, and this is perhaps a bad example. Just a second. I think I'm missing an edge essentially. Yeah, this is just this edge should have been present over here. That's what happened. My bad. Okay, so this edge should have been present over here. Basically, what would happen is that like there needs to be an edge connecting, and there needs to be a path connecting them. Where like what will happen? Let's assume for a second there's an edge over here. If there is an edge over there that the model has inferred that edge, what will happen is these edges, when they connect, they tell the system that like, okay, this entity has this property. This entity also has this property. This entity, but also has this property, which implies I can assume, I can infer that this entity over here will also have this property. So that is essentially the process of percolation happening, that like, if I simply trickle down some water on this node, the water will percolate from here to here, if there were an edge, which I'm missing right now, to here. And that would help it infer this edge, which it has not seen as of yet in its training data. Yep. Any other questions?
Great. Yeah, thank you. I have a couple of questions. Just going to double check if anyone else does. And also, yeah, if you do have a question, please feel free to unmute and turn on your camera. Or you can always type it in the chat. But for now, I'm going to ask one of my questions, which is, I'm curious with the way you've presented it here suggests that like the concepts of these kind of fixed things and the graphs learnt between them. One model I have of kind of generalized capabilities, which is learnt by these models, is when it starts using like some notion of variable, or like it has basically a circuit. So instead of it being like this feature always means man or astronaut or whatever, instead we have like some kind of placeholder variable, and then the thing that's actually been learned is like some kind of maybe Boolean circuit, which is a function from the inputs to the outputs, and then these are like slots which can represent different things for different points. Is this something that you've considered, or something that you like think you can apply this model to, or is that just an entirely different case?
Yeah. So I wouldn't say it's an entirely different case. What's happening over here as well, for example, is let's say, so let me just go back a little bit. So there were multiple concept classes over here, right? Like there's humans, animals, furniture, blah, blah. what I'm essentially getting at is that like when the process of percolation happens, to the extent that like it's still a theory, we're still confirming it, but like let's assume for a second that it happens in that situation, what I'm getting at is that the model starts to understand, because it doesn't know that these are all humans. What it'll see is like man, astronaut, stuff like that. And it just sees that like there are a lot of properties that all these entities share. So in actuality, I can just learn that there is a symbolic representation or a symbolic concept for what humans are. This is the notion of humans is something I'm imposing on the model, but like most likely the model just has a variable which corresponds to the notion of humans, and all of those, and like if you access that variable, all the properties that humans generally possess are something that the model thinks this variable that the model binds with that variable. So basically, that is precisely the reason why we suspect that even if you do not say see sentences of the sort where astronaut is running, you will still be able to infer that because you've seen a lot of other entities which belong to the human class running. And if you think astronauts belong to the human class, you will start thinking that, okay, astronauts can run. So from the point of view of circuits and variables, this is exactly what we are trying to capture here in a more implicit sense, that these classes, they have variables corresponding to them being internalized by the model, and each variable or each class has specific properties, and as long as you can access that variable, you can access all the properties which bind to that variable.
Right. I think this is a very interesting point. The thing that I was trying to get at is maybe slightly different. It's rather than saying that there's some kind of variable which exists hard-coded into the weights that like accounts for example, a class. The thing that I'm suggesting might happen when a model generalizes is a computation where the variable is something that's inferred at inference. And what I'm suggesting is that the difficult structure might not always look like some kind of ontology, some kind of connection between concepts which are fixed. Rather, the difficult thing might be some kind of computational structure. For example, there might be like an algorithm embedded in the network which sorts a list by some criteria, and it makes pairwise comparisons and uses that to sort the information. That sorting algorithm would likely, if it's learned to do it in a general enough way, be a kind of abstract sorting algorithm that can do this for any kind of object, not just objects in the human class or in the animal class, but like really any object. And so then the actual thing that's being learned is like this circuit structure, which can perform a particular algorithmic operation. And the and then the, I guess, variable concept is like really anything can be rooted into that. But maybe this is like just a different phenomenon but I'm curious if this is something that relates in a way.
Yeah, it very much does actually. So I think like there are two different things to perhaps like distinguish between here. One is like more so the knowledge the system possesses, and in some sense like what you were saying, the ontology is what the system is internalizing, and that's what like for the most part theoretically what we've been focusing on. But like once you've identified these variables, and let's say you've learned general purpose algorithms which which can operate on these variables, then in that situation, if I know that, okay, like what algorithms can operate on, let's say humans and animals, I can pass in any variable into said algorithm. So there's like a distinguishing there's a distinction to be drawn between like what between like general reasoning capabilities and general knowledge capabilities per se. This was more focused on knowledge capabilities, and once you have that knowledge, you can perform general reasoning on top of said knowledge. So in some sense, like what we show over here, this unscrambling task, it doesn't matter what sentence goes in here. The unscrambling task should technically be operable over all, like any concepts that I put in over here. And when we look at the circuits in the model, we actually see the attention maps very explicitly correspond to a precise circuitry for how unscrambling is supposed to happen. You can see that there's a precise syntactical structure that the model is inferring given these words, and it is trying to map out where, for example, like the word understood, or let's say there was a verb over here, there's a precise point where a verb is supposed to go, and like you can see that the model is inferring what the verb in this scrambled phrase is. So in that situation, it doesn't care about the variables. So there's some interaction between the general reasoning algorithm and the specific variables to operate said algorithm over. That just wasn't necessarily the main point. So hence, as of yet, I haven't included that in the discussion over here. But we have, in the paper, we will have those explicit attention maps showing, okay, the model has clearly learned a circuit to perform this task.
That's pretty interesting. Thank you, yeah. Any other questions from the audience? If not, I'll ask one more, which is, I guess, a follow-up question. Bit different, but at the beginning, you showed this example of a, yeah, like these like blue shape, the color, shape, size kind of variables, and showed that like the thing it's kind of learning is this piecewise, like and of on all of them. And there was a suggestion that, yeah, in the one slide on, yeah, if you go to the next slide, sorry. Yes, so yeah, you have the suggestions that like each of the individual properties might have a quite continuous learning curve, but then the and of them is kind of going to have this more discrete learning curve. And I'm wondering if you think that something like this might be happening in the more abstract cases as well. Like, I guess like one example is this unscrambling task. This unscrambling task seems to me like intuitively it's difficult to think of how you might decompose it into a series of subtasks it's doing a lot of, like in doing a combination. But is there some notion that this is happening as well in those tasks?
Yeah, so it's hard to define a metric which captures like how much the unscrambling circuit is ready. So you can just look at the attention maps and just by vibes you can tell that, okay, like around the transition point seems like the attention map makes sense. But that's not like a quantitative metric that I can plot. And here, however, we were able to plot it because we had proper control over the images. And we could check that like there was a bottleneck concept. Basically, the color concept bottlenecks the learning. So when there is even a single atomic ability which has a slower learning dynamic compared to the other ones, it'll necessarily lead to as a consequence lead to like the overall process slowing down. So yeah, what I'm getting at is that like as you were asking, like for more abstract and more natural scenarios, like do we expect this to check out? I do expect like this is happening all the time in real models because like real models, like most of real data is compositional in nature, and like the learning dynamic corresponding to individual concepts is going to be completely different. It depends. Like not all concepts are being learned simultaneously at the same speed. So I suspect like that's actually driving a lot of the emergent learning curves that we see in real data. And defining a decomposition in general is going to be quite difficult. Yeah. But it is actually, I would argue, a fairly solid thing to try. For example, if you've seen the arc-evals benchmark for autonomous replication, I really like the idea that benchmark went for, where they decompose how autonomous replication should be thought of into like several subtasks. And and what they argue for is that like rather than tracking the overall ability of a model to perform autonomous replication, which is somewhat hopeless right now, look at the individual capabilities which are instrumental towards the ability to autonomously replicate. And I think like that's precisely the point I want to make from these results, that like if you can define a decomposition, try to track the decomposition itself, because that's perhaps like a stronger signal towards like what the overall abilities of the model are, because more or less always it will learn how to compose said capabilities and just perform things which we did not expect it to perform.
Yeah, I'll let David take the floor.
Yeah, this graph makes me wonder, did you ever see cases where the different sub-capabilities emerged in different orders? Because to me, that would be kind of interesting to understand.
Yeah, so I intentionally wanted to keep it a little bit high level so that I didn't go through those things in detail. But like, okay, so in the first project, we consistently saw color is learned last. And it always has this like weird dynamic of like learning with this like slow speed and then like suddenly gets learned. However, in the second project that I was talking about, here what we found was there is a certain measure we can define, which again is written over here as color concept signal. Like this concept signal allows us to control how quickly color is learned. You can define the same like this thing for other concepts as well. So we can define a size concept signal as well. But basically, if the concept signal for color is low, then in that situation, the model learns about size first. And hence, like you see, the learning curve goes towards size. It goes towards like first learning about smaller circles, and then it starts to like learn about, then it starts to learn about colors. But you can actually make the concept signal for color quite large. And in that situation, the model first learns to go in this direction. It learns about, it learns how to create large blue circles, and then it learns how to change size. So basically, we consistently saw learning curves of this sort, where like there is one concept which is always the bottleneck, but we can change by performing that intervention using the concept signal variable, whether it's size which is the bottleneck or color which is the bottleneck. The weird and interesting phenomenon, however, is that like always, whichever thing we make the bottleneck always has this learning dynamic where like it has slow progress first and then like sudden learning happens for that concept. That part, as of yet, we don't have a clear, like a proper clarity of like why that is happening. Like I would have expected as we sweep the concept signal, like perhaps some point like color also starts to get learned in a continuous way with size and shape, but that didn't happen. So we still need to investigate that part more, but we are able to control whether it like, size happens first or color happens first. Yeah.
I have a really open-ended question. Is there a connection, since you're into also brain research, is there a connection to neuroplasticity as well? I could imagine there might be, like, when you say you're encouraging the latent space to go in some directions, it almost to me has sort of a conceptual hint there that you're guiding it to learn in certain directions.
Yeah, I don't think so. I haven't like actively thought about this before, but like if I just take a jab at it on the fly right now, I'd say like it's not like a big stretch. We are actively changing the training data to increase the signal corresponding to one of the concepts, and make said concepts more, let's say, more informative to the model. That's actually literally how the concept signal is defined. If you look at the mathematical definition, it's defined like in terms of information gain coming from a concept. And yeah, I'll basically have to think about that beyond that point. But yeah, that doesn't seem like a big stretch. Yeah. Any other questions? I see somebody's posting in the chat. Okay. Yeah.
Nice. Okay. I guess we're at 1.5 hours, which is a pretty good time. This was very, very informative. Thank you so much. I'm very hyped for this research in general, so thank you for this. There's also just a lot packed in there. And like each individual piece is very cool, but just the sheer amount I'm very impressed by. So thank you very much for that.
Yeah.
I guess I'll give people another like 30 seconds to come up with a question if they want to, given that we have the time, but otherwise we can wrap up. Right, I'm guessing 30 seconds, but I'm guessing that's like roughly it. Yeah, thank you so much. I guess thank you everyone for attending as well. And to those watching on YouTube, hello. And yeah,
Thank you so much
there's a
for
bunch of
inviting me. This was quite exciting. Yeah.
good stuff.